Welcome to this explainer. Okay, so how exactly do you smoothly cool a massive industrial engine without tearing the whole thing apart? You know, when you think about giant earth movers or those massive commercial vehicles, managing the intense heat of their engine seems like a job for pure brute force. But, believe it or not, the secret to taming a roaring multi-ton engine actually comes down to a microscopic layer of fluid and some seriously complex math. Today, we're diving into an absolute engineering marvel, the Hydro Viscous Clutch. We're going to take a journey from the giant macro scale of heavy machinery right down to the microscopic world of applied physics. We'll be looking at a fascinating new dynamic model that researchers developed to solve a huge problem in regulating the speed of fan drive systems. It's honestly a perfect example of how fixing just the tiniest, invisible mathematical flaw can save massive machines from total, catastrophic failure. All right, let's quickly run through our roadmap for today. Number 1, the heavy vehicle cooling problem. Number 2, inside Hydro Viscous Clutches. Number 3, the flaw in old math. Number 4, the micro ring solution. Number 5, the 3 stages of friction. And finally, number 6, smarter clutches, safer vehicles. Let's get right into it. Section 1, the heavy vehicle cooling problem. So when you're dealing with high-power vehicles, managing that engine temperature is incredibly high stakes. You can't just flip a giant cooling fan on and off at full speed. It just doesn't work like that. Without a perfectly smooth, stepless way to regulate that speed, these engines face some seriously scary risks. Research actually shows that the intense mechanical stress and torque oscillation can cause catastrophic macro-friction fractures in vital parts, like cylinder head valve bridges. I mean, just imagine the sheer amount of force it takes to literally crack heavy metal. That's exactly what happens when these fans engage too aggressively or start vibrating out of control.
Moving on to Section 2, inside Hydro Viscous Clutches.
Now, the vital bridge between that roaring engine and the cooling fan is something called the Hydro Viscous Clutch, or HVC. And what's cool is it doesn't use standard gears clicking together. Instead, it transfers power, or torque, using the sheer force of a super thin oil film, combined with the microscopic physical interaction of the clutch plates themselves. Engineers actually call those tiny surface bumps asperities.
If you picture how this works axially, you've got a separated plate on one side and a friction plate on the other. And right in the middle, there's a tiny gap filled with a really crucial layer of lubricating oil. By squeezing these plates closer together or, pulling them apart, the clutch basically acts like a highly precise mechanical dial. It uses fluid dynamics to control exactly how much power gets transmitted through that oil gap.
Section 3, the flaw in old math.
For the longest time, these clutches had a really annoying problem. They'd engage in this jerky, unstable way. The fans weren't starting softly, they were literally jittering. And the culprit? Well, the traditional math they were using was just flawed. The old method calculated the oil groove geometry using a flat, fixed contact area ratio. It basically assumed the oil was doing the exact same thing everywhere on the plate. But here's the reality check. At incredibly high rotational speeds, you get this gyroscopic effect. The centrifugal forces are so strong that they actually cause the oil film's coverage area to shrink. The old math completely ignored this shrinkage, which led to some massive miscalculations in how much load the fluid could actually bear at high speeds.
Section 4, the micro ring solution.
To fix this flawed old math, researchers came up with a genuinely groundbreaking method. It's called the discrete micro-ring area ratio, or DMAR for short. Instead of just doing one lazy, flat calculation for the entire plate, DMAR mathematically slices the clutch's friction plate into these tiny, microscopic concentric rings. It's kind of like a giant puzzle. By analyzing these little microelements one by one, all the way from the center out to the edge, engineers can figure out the precise area of the contact platforms and calculate exactly how the oil flows, no matter the speed. And this absolutely matters, because friction plates have these really intricate oil groove structures cut right into them. They definitely aren't just for show. Different radial groove patterns directly change how the lubricating oil flows. Because the area distribution of these grooves isn't just a simple straight line, shifting from one pattern to another completely changes the load-bearing capacity at a microscopic level. Using the DMAR method is literally the only way to accurately map out all that crazy complexity. To really put this into perspective, just to give you an idea of the sheer computational horsepower needed here, the researchers couldn't just use a simple equation. No way. They had to build a 32-degree of freedom dynamic model of the entire fan drive system. That means they were tracking 32 completely different, independent ways the system could move or vibrate, just to capture how these tiny micro-variations in the oil grooves affected the entire clutch's engagement. That is wild.
Section 5. The 3 stages of friction.
Now, the way a Hydro Viscous clutch actually engages isn't just an instant grab, it's more of a physical slip-and-slide journey. It kicks off in the separated stage, which is governed by fluid lubrication. Think of it kind of like a car tire dangerously hydroplaning over a puddle of water. There's absolutely zero physical contact, just fluid. Then, as the pressure starts to build, we move into the slipping stage, or mixed friction. The oil starts getting squeezed out, and the rough, microscopic peaks of the metal actually start to graze against each other. Finally, we hit the locked stage, or boundary friction. Almost all the oil is gone and the plates lock together tightly, just like solid rubber gripping a dry road.
If you visualize this load-bearing transition, you start with fluid lubrication, but then that slowly gives way to mixed friction. Those wavy, jagged patterns you might imagine represent the microscopic surface peaks, those asperities we talked about earlier. As the plates squeeze together, the load shifts. It goes from being completely supported by the fluid to being shared by the actual physical contact of those tiny, jagged peaks. Getting this specific transition smooth, that is the whole ballgame right there.
And finally, Section 6, Smarter Clutches, Safer Vehicles. When engineers actually use this DMR mathematical model to properly design those oil grooves, the real-world benefits for heavy vehicles are absolutely massive. First off, it stops those dangerous, self-excited vibrations that pop up at the friction boundaries, what engineers refer to as the Strebeck curve. Second, it lets them accurately predict the exact amount of axial engagement force needed. This is what guarantees those highly stable, soft starts for the massive cooling fans, entirely wiping out those violent torque jitters. At the end of the day, getting this microscopic math right optimizes the lifespan of the entire heavy vehicle engine, preventing the very fractures we talked about at the start of this explainer.
It is just incredible to think about, right? The difference between an engine running smoothly for decades or literally tearing itself apart in a matter of months comes down to understanding how oil flows through microscopic grooves on a piece of metal. It really makes you wonder, what other hidden microscopic engineering flaws are out there just waiting for a new mathematical model to completely revolutionize other massive industries? Thanks so much for joining me for this explainer. Keep asking questions and always keep looking closer.